we're going to talk about some of the practical implication issues involved with nuclear electricity. And in particular, we want to compare the risk of something that can happen with nuclear with the certainty of the damage caused by coal all the time. And with respect to proliferation, nuclear proliferation, what makes plutonium special and very dangerous? We want to be able to distinguish between the levelized average cost to produce nuclear electricity and the cost of operations and fuel once the facility is already paid for. So many people are motivated by fear when they think of nuclear. And there's every reason to be fearful when we think of some of the things that have happened. The first in 1979, there was a partial core meltdown at Hershey, Pennsylvania in the 3 Mile Island accident. Here we see Jimmy Carter touring the facility. To make matters worse, a movie came out that year called The China Syndrome, which is a fictional tale of when a nuclear reactor melts down and metaphorically melts down to China. It's worth noting that there were no deaths from this incident and a negligible amount of radiation was released into the environment. However, in 1986, there was a true disaster with the explosion in Chernobyl, with the meltdown and many deaths. And then, just 2 years ago in 2010, after a tsunami took out the cooling capability for a nuclear reactor, there was a meltdown and explosion. And although there were no immediate deaths, there were and will be many related fatalities. So you're welcome to feel fear, but what I hope to do here is put some numbers and facts behind some of the risks involved whenever we generate electricity. So the United States presently generates about 21% of its electricity with nuclear, compared to, for instance, 51% with coal. And both of these occupy the realm of base load. And so it's appropriate to compare nuclear with all of its costs and risks and benefits with coal. And while there are risks of nuclear disaster, the coal industry results in many deaths both inside the industry and publicly every year. This graph shows the increase in electricity generation for different technologies over the years, and we see that nuclear continues to rise despite the fact that we've had no new facilities come online since 1996. Part of this is because of the increasing capacity factor. So the people running these facilities are getting their act together a little more every year, and rather than running them at 55% of the time in 1980, the capacity factor is 90% now. This is a table of when facilities have come online. So what do other countries do? Germany uses a lot of coal. France does not have a lot of coal, and they have replaced their coal generation with nuclear over the years. We bring up the issue of variability and dispatchability. Nuclear is largely neither. Nuclear is on pretty much all the time. We don't increase it, we don't decrease it. It doesn't usually go out. So it's not variable like the wind, which can change with the wind. And it's by and large not dispatchable in that if we need more electricity, nuclear is not the facility that we're going to want to turn up or turn down. There's an exception to this. In France, there are some load-following nuclear facilities that can decrease their power output to about 60% in ramping over many minutes. However, in the United States, and by and large worldwide, nuclear is baseline. It's always on 100% of its capacity, except for when it's taken down for changing of nuclear fuel rods or some other maintenance issue. Incidentally, a lot of these slides have been taken from 2 talks I've seen by Per Peterson, who's in the Department of Nuclear Engineering at Berkeley. We can look at the industry deaths related to coal mining. For coal, between 1980 and 1990, we have about 30 deaths a year on the surface and 60 deaths a year underground. And we note that only 31 workers died in Chernobyl. However, all of these numbers are grossly understated. The nuclear disaster at Chernobyl will likely kill more than 4,000 people in cancer and related diseases from the radiation exposure. And so what we see is the eventual deaths from the effects of a nuclear accident are much, much greater than the immediate deaths in the disaster. We can look at an article recently that claims 14,000 U.S. deaths on the west coast of the United States are tied to the Fukushima disaster. So these are large numbers, but what do we compare them to? There are likely more than 50,000 deaths a year in the United States resulting from the burning of coal. With coal, we have environmental destruction from mining, and we have respiratory related deaths from the burning, and of course a large amount of greenhouse gas emissions. With nuclear, we have similar mining concerns because you have to mine uranium. You have a small possibility at any given time that a nuclear disaster could cause a loss of a significant amount of lives, and we also have nuclear waste that we have to deal with. Here we look at greenhouse gas emissions in grams of CO2 per kilowatt hour for the different technologies. Red represents the direct emissions from burning fuel, and white represents the related emissions, the life cycle emissions per kilowatt hour, resulting from the building of the facility and all other related operations. The two different numbers refer to different estimates, a high estimate and a low estimate. I've seen other estimates that put nuclear at higher GHG emissions than wind. Nevertheless, nuclear is certainly very low emitting for greenhouse gases compared to coal, which is the other baseload alternative. Uranium. It's mined as uranium oxide, and it's worth noting that less than 1% of it is fissile. This is the uranium we want to power our facilities. Almost all of it is U-238, which is non-fissile, but it's fertile. What we remember that means is that when it gets hit with a neutron, U-238, it doesn't fission like U-235 does, but it accepts that neutron, becomes Plutonium-239, which is fissile. It's worth noting that if we double the price of uranium-235, like many other mined resources, we can expect a tenfold increase in the availability of it. And because the cost of uranium is very small in the generation of electricity compared to the capital cost, it will minimally affect the cost of nuclear electricity. And so what this means is we're not in any great worry of running out of nuclear fuel, because its price could rise considerably without electricity, nuclear electricity, becoming more expensive. And that would make available technologies that would mine much, much more uranium. Here's where uranium is mined in the United States. And just like with any other mining, there's going to be an environmental conflict here where there's a dispute over whether or not they should mine uranium near Grand Canyon. So most of the uranium is 238, which we don't need. What happens to it? We call this depleted uranium. It is toxic, so it must be stored safely. It's used a lot by the military, both for armor and armor-piercing ammunitions, such as these bullets that are tipped with uranium because it's so dense, it's more likely to pierce armor. It's worth noting that about 1,000 tons of depleted uranium were used in about 3 weeks in Iraq, and this uranium is distributed all over Iraq, and there are environmental concerns thereby as well. When a fuel rod is no longer useful, a good portion of the 235 has been used up, but there's still some left. Additionally, a lot of the uranium 238 has been transmutated to plutonium, and we want to extract that. So the question is in this processing, what would happen if some of the material disappeared? And this is a very important issue as far as proliferation. When we talk about proliferation, we talk about the spreading of the ability to make a nuclear weapon. And this is something that we're concerned about. When we process spent fuel rods, we want to do it to recover the U-235 or the plutonium from the uranium-238, which is the majority of the uranium. Now, we don't want this to fall into the wrong hands. The reason is because The purification of U-235 to make nuclear weapons is the biggest challenge in producing the nuclear weapons, because 235 and 238 are chemically identical and they have to separate them using their different masses. And they're very close to the same mass. It's very hard. So for the Manhattan Project, they use membrane diffusion, and presently, more and more, we're using ultracentrifuge separation. However, plutonium is chemically distinct from uranium, and it can be separated very easily using chemical methods. Plutonium doesn't exist naturally, so it's no problem unless someone gets a hold of a spent fuel rod. So to summarize, it's very difficult to purify a fissile material to make a bomb. This is because plutonium doesn't exist naturally. However, if someone got a hold of a spent fuel rod, they could relatively easily isolate the plutonium and make a bomb. So we need to be very careful about processing spent fuel rods. And actually, in the United States, we've decided it's not worth the risk, so we don't process spent fuel rods. We just dispose of them. We'll talk about disposing them in a minute.